We've seen that functions are a convenient way to express the relationships between various variables. We've looked at various types of functions, including linear functions. In this video, I want to tell you about a few properties of functions that we economists are often interested in. Specifically, the properties that I'm going to talk about are monotonicity, continuity, concavity, and convexity. Let's start with monotonicity. So this function that I've represented by this red curve is a monotonic function. Specifically, it's a monotonic increasing function. What that means is that as we increase x, the value of f of x also increases. Another way to think about this is if at any x, if we look at the derivative of this function at any x, remember the derivative is the slope of the line that's tangent to that curve, it's sloping upwards, which means that the derivative is positive. When we just say monotonic, we mean that it's always either greater than 0 or it's always less than 0, but it doesn't fluctuate. When we say it's monotonic increasing, that means that the derivative is always positive, so this curve is always going up. Here's an example of a function that's not monotonic. It goes down, it goes up, it goes down. So if we were to look at the derivative, sometimes it's going to be a negative number because the tangent is sloping downwards, and sometimes it's going to be a positive number. The tangent is sloping upwards. The next property of a function that we're going to look at is what we call continuity. Let's go back to that curve that I drew earlier, and we see it's this nice shape. There are no cuts or breaks or jumps in it. So what does it mean for a function not to be continuous? Something like this is not a continuous function. Very loosely speaking, if you were to draw it, you'd have to pick up your pen to do so. So at this point right here, the function jumps down as we move from left to right. This is not a continuous function. Another useful property of a function is that it takes a shape like this, where it's kind of a hump. We call that concavity. Notice that as we move to the right, we start with a derivative that is positive, so the tangent is sloping upwards. It flattens out as we go, and then after it's flat, it starts to go down. So the derivative, remember that the derivative is the slope of the tangent, it's always decreasing. Since the derivative is decreasing, the derivative is a monotonic decreasing function. As we saw when I described monotonicity, a function is monotonic increasing if its derivative is positive. Similarly, it's monotonic decreasing if its derivative is negative. So if the derivative of this function f is monotonic decreasing, what that means is that the derivative of the derivative is negative, or less than 0. You may recall that from your earlier math courses that the derivative of the derivative is a second derivative. So a concave function is one where the second derivative is negative. Well, what if it were a monotonic increasing function? That's what we call convexity. To the left, the tangent to the curve slopes downwards, has a negative slope. It flattens out as we move to the right, and then it starts to slope upwards. So the derivative of this function, f, is increasing, meaning that the second derivative is positive. And that's what we call convexity. Why do we care about convexity and concavity? Here's an example of a function that's neither convex nor concave. At first, we see that the slope of the tangent, or the derivative, is increasing. So we might think, this looks like a convex function. Things look good until here, but then they start to decrease again. So this can't be a convex function, but since it was increasing, it couldn't be a concave function either. So this function is neither. We see a lot of convex and concave functions in economics. Why do economists like these things so much? It's because we can find the maximum or the minimum of these functions. Specifically, if a function is concave, we can find a maximum. We can find the highest point. And if a function is convex, we can find a lowest point, or a minimum. So if we look at this concave function, for instance, this point right here gives us the x where f reaches its highest value. And that highest value is here. So if we have this concave function, we're able to find the point that maximizes f. What we're doing is just finding the flat part, the part where the derivative is 0. So if the function is concave, like in this picture, that flat point gives us the maximizer. On the other hand, if we had a convex function, the flat part gives us the minimizer. So most of the functions we're going to work with are going to be either convex or concave, and we'll be finding either the minimum or the maximum respectively.